Memory layout is a must-have for those who work with low-level frameworks like Metal, and it's also useful for increasing developers' knowledge. Let's start with a few words about how data is stored on a computer. All data is represented as a combination of zeros and ones. 1 and 0 represent the presence or absence of a charge on a transistor. The smallest unit of memory is 1 bit, which can take either a 0 or 1 charge value. A single bit is not so interesting due to its small size, as it can only have two values, 0 or 1. Therefore, bits are organized into bytes. A byte is a combination of 8 bits. Each bit in a byte has an independent value, either 0 or 1. If we do some math, a byte can have values from 0 to 255, a total of 256 values, because it is 2 to the power of 8. However, we cannot read individual bits or bytes from the memory. The minimum memory size we can move our pointer to is one word, which is a combination of 8 bytes. In computer science, a word refers to the amount of information that fits into a single pointer. Whether we like it or not, with a single memory access, we always read 8 bytes or 64 bits. Have you heard about 64-bit processor architecture? That's precisely about reading 64 bits with a single memory access. There are certain rules to efficiently manage these 64 bits. The summary of these rules is called memory layout. In Swift, memory layout is a enum that contains three main static properties: size, stride, and alignment. Size is the number of bytes occupied by our data from the first to the last. As an example, let's consider a structure called SUMSTRUCT that contains two fields, int32 and bool. int32 occupies 4 bytes, and boolean field occupies 1 byte. Technically, the boolean field only occupies 1 bit, but the minimum memory size is 1 byte, so the boolean field actually occupies a full byte. Now let's look at the layout of the structure within one word. The first 4 bytes belong to the int32 type, and the fifth byte belongs to the boolean property. Thus, the size of the structure is 5 bytes. Let's complicate this example. Here is a new struct called another struct. Its first property has an int32 type, the second property also has int32 type, and the third property is boolean. The first two properties together occupy 8 bytes, and one boolean property occupy only 1 byte. Hence, the size of our structure is 9 bytes. Note that the structure doesn't fit a single word. It occupies only one full word and 1 byte from the second word. Therefore, we'll have to read the structure in two memory accesses. With first memory access, we'll read the first word, and with the second memory access, we'll read the second word. The next thing to learn is stride. Stride is a number of bytes of the word that contains the data. Our sum struct from the first example fits within one word. One word holds 8 bytes. This means that the stride of the data of this structure is 8. The second structure, even though it only slightly exceeds one word, occupies 2 words. In 2 words, we have a total of 16 bytes. This means that the stride of this structure is 16. Alignment is the most interesting part. The purpose of alignment is to obtain the maximum amount of data with the least number of memory reads. Data that occupies 8 bytes can be stored in memory in different ways. Let's consider the memory layout in the top and the bottom diagrams. If we arrange the data as shown in the bottom diagram, we would have to read two words, word 0 and word 1, to read this data, which means two memory reads. But if we pack our data in a way that it completely fits within one word, we will only need the one memory access to read this data. It's easy to guess that alignments of simple types like int, string, bool, and so on is equal to their size, simply because they need to leave space for themselves to fit within one word. The alignment of complex types, such as structures, is equal to the maximum alignments of their properties. That's something to remember. Let's go back to the first example and consider this structure from an alignment standpoint. In this case, there is enough space for all of the properties. int32 starts from the 0 byte, and boolean property can start from any byte. If we swap two properties, meaning the boolean property comes first and then the int32, we will see a significant change. The int32 property will have to move to the 4th byte. The property should start with a byte with the index that is multiple of its alignment. Therefore, the int32 type can start from indexes 0, 4, 8, 12, 16, and so on. The 0 byte is already occupied by the boolean property, so int32 shifts to the 4th byte. That rearrangement will affect the size of the structure. We can see that the first structure was assembled more efficiently because its size was 5. By swapping the properties, the size of the second structure increased to 8 bytes. We have 3 empty bytes that are not occupied by anything. Fortunately, you don't have to manually calculate the data layout in the memory because Swift provides us with the memory layout enum mentioned at the beginning. Using this syntax, you can find out the memory layout for any type. To reinforce this knowledge, I recommend you go into a playground and play with memory layout. If you have any questions, feel free to ask us in the Telegram chat. That's all for today. Goodbye.